So what we've seen is that two groups had gone through and made painstaking measurements of effectively the spectra of stars over time. And by making those measurements with exquisite accuracy of wavelength, they were able to use the Doppler shift to convert the shifts in wavelength into velocities. And when they did this work, they discovered planets.
But these are weird planets. I mean, these are nothing like our own solar system. In our own solar system, the big, massive planets like Jupiter, Saturn are a long way out. But here we're talking things with the comparable masses of gas giants, but either practically skimming the surface of the star or in highly eccentric orbits very close in. So that's very weird.
Well, you say it's weird, but who's to say our solar system should be typical? I mean, why would we not expect to have these types of planets out there?
Well, the reason why people didn't expect these sort of planets is because of what's called the snow line theory. This is a theory of how gas giants form. If you remember when we talked about solar system formation, the idea was you start off with tiny little grains of stuff that's stuck together to make bigger and bigger lumps until eventually they end up with planets. Now, in the inner solar system, the only lumps we can have are lumps of rock. But in the outer solar system, where it's colder, you can have lumps of ice. And because ice is mostly hydrogen, there's a lot more hydrogen out there. That's the most common element in the universe. So there should be a lot more ice out there than there are rocks closer in. There's also rocks further out as well. What this means is that planets further out in our own solar system, the snow line is probably somewhere in the asteroid belt. Things beyond there should be able to get much bigger because they can be made of ice as well as rock. In the inner solar system, the ice will just all evaporate away. So what that means is the planets further out should get bigger. Not much bigger, maybe 3 or 4 times bigger. Once they're 3 or 4 times bigger, their gravity is stronger, and they can then start sucking in all this hydrogen and helium gas that's around, at which point they get very much bigger, like 300 times bigger, like Jupiter is. So this is the standard theory, and this said that you should only be able to form really big planets out beyond the snow line.
Okay, so we have a mystery on our hand of why we have these objects, these gas giants, right next to their stars. And so, once again, another mystery confronts us. So how are we going to solve this?
Well, clearly we're going to need more data and some good theoretical thinking, and that's what we'll cover in the next lesson. So, we have a real problem. As the light from the telescope comes into the spectrograph, it'll shift around due to atmospheric seeing, which will affect where it lands on the slit, which will affect what wavelengths we actually measure, and will give us spurious apparent motion of the star. So how do you overcome this? Michel Mayor and Didier Queloz from the Observatory of Geneva came up with a solution to this. The solution was to use something like this. This is optical fibre cable, a glass cable, in this case encased in plastic to protect it. What happens is if you shine light in down one end of here, like I'm doing now, light will come out the other end, as you can see. So it's coming in here, it's going all the way around the loop and coming out over here. The crucial thing about that is it doesn't matter exactly where on this end the light goes in, the light coming out remains very much the same. So this is perfect. What you can do is put one end of this at the focal plane of the telescope, where the slit would normally go, feed the other end into the spectrograph, and no matter how the light jiggles around, by the time it's travelled all the way around the loop of optic fibre, it's been randomised and comes out perfectly uniformly. So that gives us the stability we need to actually see things, see these very small shifts in radial velocity. The second problem was the problem of needing a reference position. Shift relative to what? And once again, spectroscopy can help. The idea is to use something like this, a arc lamp. In this case, it's a sodium vapor lamp. A voltage is applied through a gas cylinder containing mercury or cadmium or some other, in this case, sodium at very low pressure, and it causes it to glow. In this case, the characteristic orange glow that you often see in street lights. But this is always going to be at the same wavelength, the emission lines of sodium, in this case, the sodium D lines. So what you can do is get a second optic fibre and feed the light from this down that second optic fibre into the spectrograph. So what you'll find in your spectrograph is 2 spectra. A spectra of your star, which will be shifting, and a spectrum of this, which won't shift. All the change in the slit will be taken out by the optic fibre, and so by referencing the two, you should be able to get a really, really precise measurement of any relative shift of the star compared to something which isn't shifting, the lamp which is sitting in your telescope on Earth. So this is the technique they use to get the precision down to a fantastic 30 meters per second.
So Paul, you've shown us that by being smart, you can go through and really design around all of the problems, perhaps, that are facing us and doing this experiment. So you can use a fiber bundle to scramble things so that even though the star is moving around, we get all of its light all the time and it won't mess up our observations.
And a couple of groups had figured this out by about the mid-1990s, and they'd got the precision down to a staggering 30 meters per second. So you could look at a star and measure its velocity to 30 meters per second. Now that still wasn't good enough, staggering though it was, to find planets, because remember Jupiter's only going to cause the Sun to wobble by about 10 meters per second. So they weren't expecting to see planets. What they were actually looking at was companion stars, the idea being that around a normal star there might be a small, say, red dwarf or brown dwarf star orbiting it.
All right, so like all good things in astronomy, or maybe not all, but almost all, you're out doing a very simple experiment. And in this case, they were looking at a nearby, quite bright star, known as 51 Peg, as we shorthand called it. And it's a fairly ordinary sun-like star, relatively close, so it's nice and bright. And you can go out and hopefully see what's going on around it. But they found a bit of a surprise, right? Because it wasn't just sitting still or not moving at all, and it wasn't moving a lot, it was moving a bit.
So here's what they found. Here's the velocity of the star against time. And what you can see is that, to begin with, it was moving at about 120 meters per second. And when they observed away from us, when they observed it next time, a few days later, it was about a velocity of 0. And then it changed, then it changed, then it changed, then it changed. It was jumping all over the place.
But it's changing very quickly. It's changing on an order of a few days, not months or years like we expect planets to be.
Yes, it seemed to be a 4.6 day period. Remember, Jupiter goes around the Sun every 11 or 12 years. This is 4 days. And the amplitude is enormous. Remember, they were not expecting to see planets. They were expecting to see a planet would cause about a 10 meter per second shift, which was within their uncertainties here. What they were actually picking up, however, was much bigger. It would shift by plus or minus about 75 meters per second. So talking about huge velocity shifts on an incredibly short time scale. So what's going on here?
Well, it seems like we need to go through and use the mechanics that you've put forth and calculate what type of object could do this.
So what are the properties of this planet around 51 Peg? I'm going to work out the properties as they would have been worked out by Mayer-Onkelos back when first discovered. Since then, our measurement of the period and velocity has changed a bit, so the answers you see nowadays are a bit different. But the numbers they had to work with then were a period of 4.63 days. We now know it's a bit shorter than that. Velocity of the star of 74.5 meters per second, and a mass of the star, 51 Peg itself. You need this to work out anything else. It's worked out from normal stellar modelling of 2.2 by 10 to the 30 kilograms, so 10% more massive than our own Sun. Now, given those numbers, we can use the equation that the radius of the orbit is the cube root gm1 period squared 1 over 4 pi squared. Plug these numbers into here. Remember to convert days into seconds by multiplying by 24 and 60 and 60. And that comes out as about 0.05 astronomical units. Very close in. 20 times closer in than the Earth in our own solar system, let alone Jupiter. How about the mass? Well, remember we can't actually work out the mass. We always work out as m sine I. If it was edge on, we have the equation that v equals 2 pi over p r m2 over m1. That rearranged to make m2 the subject, we get m2 equals m1 p over 2 pi r v1. That's edge on. If it's not edge on, we don't know it's edge on, that should actually be m2 sine of the inclination angle equals all that. Once again, plug the numbers in, and we get m2 sine I is 1.25 by 10 to the 27 kilograms, which is somewhat less than the 1.9 by 10 to the 27 kilograms that is the mass of Jupiter. So this is turned out about half the mass of Jupiter if it's edge on. If sine I, so if I is 90, then the mass is about half the mass of Jupiter. If I is larger or smaller, then the mass will be bigger. So what we've learned is that if, it's a big if, this thing is in a nearly edge-on orbit, it's going to be something about the mass of Jupiter. So there's, like shown, that dot here. Maybe half the mass of Jupiter, maybe 2 times the mass of Jupiter, depending exactly what the angle is. Here's an actual scale diagram of it here, and you can see just about the dot. Here it is.
Coming towards me.
Yes.
It's not very big compared to its star.
Yeah, you often see artist impressions showing it look very big and very close. This is actually a true scale diagram. This doesn't look like it's very close, but in our own solar system it would be much further away. You wouldn't see it at all. So this is actually what it looks like. It is much closer in, about 10 times closer than any of the inner planets in our own solar system, let alone where Jupiter is.
All right, so Paul, this is well and good, but you have said edge on. Couldn't it also be the other direction, so that it is face on, so that the planet is moving in the plane here of our screen, like this one, so that in that case, the motion of this star, the radial velocity is very small, and so you have to have a much bigger object, like a star rather than a planet, to account for what we see.
Yep, so this is entirely possible. It could be that it's actually not a planet orbiting, but something much more massive like a red dwarf star like I've shown here. But for this to be the case, the orbit would have to be very, very precisely within a degree or so of being face-on, which is actually quite a coincidence. If it's more than that, the radial velocity would be too great, because a thing like this would have much more mass. So it would take a fair coincidence that it was so precisely face-on.
And they didn't look at thousands of stars to find this, right? They only looked at a few, so it's not like we're just selecting the one out of a thousand objects. It really was out of a few. So the odds are that it actually isn't this. It really is a planet.
But you don't want to rely on odds like that. If it is a planet, it is pretty close on. Here's sunset from Siding Spring Observatory. That's what our sun looks like. If we were watching sunset on this planet and it really was an edge-on thing, that's what sunset would look like.
Ooh, I think it would be pretty hot on that planet by the looks of the sun being that large.
Yeah, so you certainly wouldn't be seeing gum tree covered hills down here. In fact, it probably is a gas giant planet. We know that planets of that sort of mass in our own solar system are like Jupiter and Saturn, which are gas giants, don't have solid surfaces. But we don't really know anything about this planet.
So it would be really cool if it exists, but I think the big question is it real? And, you know, so the data, as you showed, are really, really hard to get. They've had to go through and do all these little things, and, you know, let's face it, it's pretty easy to make a mistake when you're on the bleeding edge like they were.
And you don't know for sure that it's not actually a star, not a planet in edge-on orbit. I mean, probability says it's unlikely, but, you know, you'd be prepared to bet the bank on that.
And there's also forms of stars that pulsate. I study things like auroral Lyrae stars or Cepheid variable stars, and there's a whole range of different ones. Are we sure that this isn't just some form of stellar pulsation like we've seen before in a slightly different form that happens to be 4 and a bit days long?
It could be that instead of the star moving backwards and forwards, what's happening is the star is getting bigger and smaller, pulsing. And as we're looking at the near side of it, when it gets bigger, it appears to be moving towards us, and when it's becoming smaller, it appears to be moving away. So, provocative, but hardly compelling. So, at long last, we've discovered planets around normal stars. Or had we? I mean, there was a lot of reason to be sceptical about these things, and in fact a large fraction of the astronomical community were really not convinced. There had been too many false alarms in the past. What we really needed was some independent confirmation.
Exactly. Certainly from my own experience, you need to have 2 teams looking at something that's really controversial for people to believe. And in this case, a team in California had come up with a novel idea to really make sure that they didn't have any what we call systematic errors. Because if you remember, when you need to measure these tiny little velocities, any little tiny glitch will give you the wrong answer. And so what they decided to do is they put a glass cell full of iodine. And now iodine has lots of spectral lines, like thousands upon thousands of them. And they're very narrow, and they put it before the light entered the entered the spectrograph. And so as the starlight shone through this iodine cell, it had imprinted on it each of these lines of iodine, which could act as a reference stick for the wavelength of the light.
So the spectrum you see at the end here would have both the lines from the star itself and the lines from iodine. Now the iodine cell is not moving, so if the spectrograph was all perfectly stable, they would always be in the same place. In practice, as the light lands on different parts of the slit, or the temperature or the pressure change, or any of the other things that could go wrong, that would cause the iodine lines to shift a bit, but it would shift them by the same amount it would shift the lines of what you're looking at.
That's exactly right. So it was a way of getting rid of all those nasty little problems. The trick is these iodine cells are messy, and they really do make a nice looking spectrum and make it look terrible. So it's very difficult data to analyze.
So a lot of hard work had gone into the software.
Yes.
But nonetheless, the Californian group of Paul Butler and Jeff Marcy had been working on this, and in fact they actually observed 51 Peg. They just hadn't analysed the data, because after all, no one was expecting planets. They didn't think we could see planets like our own solar system. But as soon as they heard the result from Switzerland, they of course immediately went back and analysed the data, and they found the same thing. What's more, when they dug through more of the data, they found more similar sorts of signals. So at long last, we had confirmation.
And we didn't just have one object, we had a whole bevy of planets suddenly come from essentially nowhere in a very short period of time.
So here were the three problems we thought. The first problem were the data valid, and the fact that we've now got two groups using different methods. So we have the Swiss group who are using the fibre optic cable method, and we had the California group using the iodine cell method, and they both observed the same thing and saw the same velocities at the same time on different telescopes and different methods. So that's telling us that this is very difficult observations, but clearly they're getting it right.
So Paul, we still have that problem of potentially the object just being a brown dwarf nearly face on, so you only get tiny orbital motions.
So it could be that the motions are real. In fact, they probably are now. We have two groups finding it, but maybe it's not a planet, maybe it's a star. And of course, we've known about binary stars for a long time. But the more you discover, the less likely that becomes. Because if you imagine, let's say you have something really massive going around like this. If it's face on, most of the wobble is going to be out of the, not on your line of sight, so you're only going to get a very small fraction of it. So it look like a planet. But for everyone that's going to be face on, there are going to be many more that are at some other angle. And for these ones, you're going to see a huge oscillation. And so you'd expect maybe for every one that looked like a planet, you'd see 10 or 20 that looked like brown dwarfs. And you won't see anything like that many, these huge oscillations that could be brown dwarfs. So with just one, maybe it could be a fluke. It happened to be in face on very close. But by the time you've got 3 or 4 or 5, let alone the hundreds we've got now, that doesn't make sense. Any individual one of them still could be, but as an ensemble, the whole population, no.
Okay. So what about the idea of it being some sort of stellar pulsation, like a Cepheid variable star, but something a little different, that just mimics the sine wave of a planet?
Well, this was seriously considered. Maybe it was some sort of strange pulsation of the star's surface rather than the actual whole star moving. The trouble with this were kind of twofold. First of all, when you get a pulsation from a star, it's very rarely looks like a sine wave. It tends to be a slow rise and a sharp drop, or a steep drop and a steep rise and a slow fall. Secondly, when stars pulse, they don't just pulse at one period, they pulse at multiple periods simultaneously.
They have a resonance, right? They're almost like a musical instrument that when you play a trumpet, it doesn't just give you one tone, it gives you multiple
It's a whole bunch
tones.
of harmonics.
Yeah.
Only they're not very harmonic, they're all at funny ratios. It would sound horrible if you listen to it. Probably like bagpipes.
Yeah.
Bagpipes and bells are two instruments that have harmonics that aren't nice at regular intervals. But people were only seeing the one sine wave. So that made it very hard to come up with any model of a star that would do that.
Okay, so it looks pretty solid.
And what were they discovering? Well, most of the ones they were discovering were something like this, the hot Jupiter, where a planet's in a near circular orbit very close in. This is a schematic, it's not really to scale. To scale, it looks more like this. There's a dot coming across.
Much less impressive.
Much less impressive, which is why most people don't give you scale drawings of these things.
So were all the objects, going in these close circular orbits?
The bulk of them were, but there was also another class of things, what were called the 70 Virginis systems after the the first one discovered, 70 Virginis. And these ones, the planets are actually much further out. This is, once again, is not to scale. They're actually maybe as far out as the Earth, an astronomical unit out, but they had very elliptical orbits. They came very close, whipped around very close, then way out slowly, then in and close.
So you can really see them when they come close. So the way you find these things is the fact that they are elliptical, and they have big radial velocities here, very tiny ones out there.
That's right, at least to begin with, that's how they were discovered. Okay, let's work out the predicted wavelength shift due to the movement of the Sun forwards and backwards because of a planet in a nearly edge-on orbit. So for this we want the velocity of the star. Now the equation for this is a simple one. It's just the circumference of the circle it has to travel in divided by the time taken to go around, the period. So this, remember, is r1, the radius not of the orbit of the planet around the star, but just of the little circle that's been done by the star. We've already worked that out for the case of something like Jupiter orbiting something like the Sun. And here's the period, about 12 years in this case. So we can simply plug some numbers into that, and we get a velocity for the velocity of the motion of the Sun caused by something like Jupiter of about 13 meters per second. Multiplied by 3.68 kilometers an hour, so we're talking about 40 kilometers an hour or so. So the speed of a rather slow car. Can we see this? Well, that will depend on the Doppler effect. The Doppler effect equation tells us that the change in the wavelength of light caused by the motion divided by the wavelength of the light when it's unshifted is equal to the velocity divided by the speed of light. This is an approximation valid for speeds of light much lower. The speed's much less than the speed of light, and 13 meters per second is certainly much less than the speed of light. So let's assume we're looking at a wavelength of the optical light, so say about 500 nanometers. This gives us that the wavelength shift is equal to the velocity, so 13 meters per second divided by 3 by 10 to the 8 times the wavelength, say 500 nanometers, which comes out as 2.2 by 10 to the minus 5 nanometers. So a very, very small shift in the wavelength.
So Paul, you've shown us that as Jupiter orbits the Sun, it's going to cause the Sun to go through and have a small Doppler shift, equivalent to 2 times 10 to the minus 5 nanometers in wavelength. Now that's not a very big shift.
Yeah, it's very tiny, but in principle you could put a really big spectrograph. These things typically weigh tons under the size of rooms, which can measure this sort of stuff. So you might see a spectrum with wavelength against flux per unit wavelength with, say, an absorption line, and it might move.
Okay, so it does shift a bit, and so that should be measurable, as you say, if we get enough light and data. So
the trouble is that, once again, the absorption lines are not going to be that narrow.
Yes, because stars do different things. For example, the Sun rotates at 2 kilometers per second.
Yep, so if we look at the Sun, as you said, we're not going to be able to see the star as a disk, looking at different parts of it. It's just going to be all one big blur. If we measure the spectrum of that big blur, say this part of the star, let's say we're looking from down the bottom here, this part of the star is moving away from us, that part's moving towards us. So the spectrum of the left-hand side is going to have a dip over there, the spectrum of the right-hand side is going to have a dip over here. You can't pick them up separately, because you've got to imagine looking at the combined light from all the different places across here, some of which are moving away, some of which are moving towards us. Add it up, you're going to get something that's quite broad. Having calculated how broad, so typical surface speed of the Sun is about 2,000 meters per second. The change in wavelength over the wavelength is the velocity divided by the speed of light. So 2 over 300,000 comes out as about this.
So that's almost a factor of 100 larger than the effect we need to measure.
Yep, so once again we're in the situation of going from something like this to something like that.
Well, Paul, that almost looks as hopeless as what we saw before. We were trying to measure the motion of the star, of a star like the Sun across the sky.
Yes, I mean, once again we have the problem with the photon arrival noise. It's not going to be a perfect data, but we do have a few advantages here. I mean, one advantage is the shift does not depend on how nearby the star is. The sideways shift gets smaller the further away something is, but this thing, it doesn't matter how far away the star is, the shift is going to be the same. A second advantage is you don't just have one absorption line in a star, you get thousands of the things.
Oh, so you can average over many, many thousand. Okay.
So that gives you a big advantage. And another advantage is, for looking at the wobble of a star, you had nothing to reference against. You didn't need another bright star nearby. But here what we can do is we can feed in light from an arc lamp or something which always emits at a particular wavelength and compare it against that. So we can actually build a reference right into our own telescope.
Ah, so that sounds like a big deal, because that's a big difference compared to the previous method, where we didn't really have that built-in reference. We didn't have an artificial star we could put in the sky.
So maybe it's not totally hopeless here.
Okay.
So over many years, a group of astronomers, this is not the glamour job of astronomy. You had the glamour job of astronomy.
Ah, we cosmologists have the glamour job, but these guys were stellar astronomers, right? And they were out measuring very, very precisely, being very, very persnickety in their measurements of the motions of stars, and having to really just beat down every little problem as they went along the way.
And there are a lot of problems. I mean, here's how a spectrograph works. You get the light comes in from a telescope. It's brought to a focus here. It goes through a little slit at the focal plane. Comes to a lens called a collimator, sends into a parallel beam of light that bounces off a diffraction grating. For these mammoth spectrographs, it's a thing called an echelle normally. Then that splits out the red and blue light separately. They're focused and brought to a detector where the blue light arrives in one place and the red light in another. So what could go wrong with this?
So, if we're here on Gemini North going on, you can see as the telescope's following the star across the sky, the telescope moves over, and these are made out of metal, and they're not perfectly stiff, and so they're going to bend a little bit, aren't they? They're going to actually not. Everything's not going to be exactly still.
Yeah, no matter how strong you build something, it's always going to bend a little bit as you tilt it around to point at different parts of the sky. So if your spectrograph is on your telescope, then it's bound to bend somewhat. You can try and build it like a battleship, really, really heavy, and that might minimize it. But it's, again, it only needs to move by a tiny, tiny fraction of a wavelength of light to completely muck up your observation.
But presumably we can go through and engineer the telescope to try to counteract that, right? We have this ability to put a reference built into the telescope, so that's got to help on this front.
Yeah, what's normally done here is actually you bounce the light sideways down a combination of mirrors, so you can actually put the spectrograph at least in a room somewhere else where it doesn't have to move around, or maybe run a fibre optic cable, so light goes into a fibre optic cable and runs down to it. So that means the spectrograph at least can be stationary.
Okay, so that's a big way to get rid of some of that bending light. But presumably we have another problem, which is the atmosphere. Well, we have a high and a low pressure system. The refractive index of the air isn't exactly 1. It depends a bit on the pressure. And I think, just thinking about it, that's going to cause a bigger problem than the size of the measurement we want to make.
Yes, that's an issue. Also, the temperature's going to change. You get a hot summer's day, your spectrograph will heat up, and that will make every part of it expand. And also the air inside will expand, have a different refractive index. Again, a very small effect, but even a tiny fraction of a degree is enough to move things by far bigger than the effects we're looking for.
So we're going to have to overcome these as well. It seems like you're going to have a very, very accurate barometer.
And there are also other problems they found out. For example, at the Anglo-Australian telescope, the spectrograph had the problem that they were picking up the strange noise, extra noise in the detectors. And they couldn't figure out what was happening, so they would go into the room where it was stored and poke around. They couldn't see what was causing the noise. Then they'd go out and find the noise had got 100 times brighter. It actually turned out that the paint on the walls was fluorescing at very low levels, too faint to see with the human eye. But whenever they went on and turned on the fluorescent lights, the ultraviolet photons from the lights would be absorbed by the paint on the walls. And then when they turned the lights out again, the walls would glow a little bit for the next day or so. It turned out it's titanium dioxide in the paint, which was not known to fluoresce, but does at a very low level, was causing a problem. In the end, they had to go and take every paint in the hardware shop, paint blocks of them all on the walls, and try and work out which one glowed. 'Cause it doesn't actually say on the paint can, beware, this paint will glow at incredibly low levels, do not use in astronomical spectrographs.
So when you're trying to make measurements like this, every little thing ends up making it impossible to get to that level. So you just have to control every variable. But it sounds to me like, okay, so we're controlling all these variables. You have a really accurate barometer. You get the right paint in the room. You stabilize your telescope. You use a fiber optic feed, and you have a reference.
It turns out the biggest problem was none of these. The problem was, in our spectrograph, the light comes in at this end, and here I've shown it going to the middle of the slit. But if instead the light was near the top of the slit, that means it's coming into a different angle here, hits there, a different angle, and it moves the spectrum up and down here a little bit. Once again, not by very much, but still 100 times more than what you're trying to look for.
Okay, but Paul, this is a huge problem. Clearly, we can build a telescope that will be able to track that star really, really accurately, right? So I've got a star, I need to put a slit across it, and so I go through and I write a computer program that says, there's the star, put it right there and keep it there, and I make sure my hardware is stable enough to keep it right there.
Yes, in principle. The trouble is that if you look at the star image very quickly, here's what it's actually looking like.
Ah, that's the atmosphere, the turbulence in the atmosphere moving things around.
So even if you've got your telescope perfectly lined up, the star's going to jiggle around from the top to the bottom.
And
you could, in principle, avoid this by going to space, but the trouble is you can't actually get spectrographs this big in space. The spectrographs on space telescopes, you simply can't have a many-ton, 10-metre-long spectrograph on a space mission. They won't fit in the nose cone of the rocket. So we have to do this from the ground, and this is going to cause our image to jiggle around all over the slit.
All right, so these things, I know the atmosphere moves around at like 1,000 times a second, right? So that becomes pretty difficult to control. So how do we end up controlling this? Seems almost impossible. So Paul, you've shown us that if we were to look at a solar system like our own, with Jupiter going around the sun, very nearby, 10 light years away, that the sun would be wiggling by 0.0016 arc seconds. Now, an arc second is, there are 60 arc seconds in an arc minute. Well, an arc minute then has 60 of those to make a degree. Now, degree, I think, is something we understand. So an arc second is 1/3600th of a degree, and this is almost 1,000th of that. So this is a very small angle, but of course we have big telescopes that are very precise. So how does that seem like we're going to be able to do that?
Well, in principle, you might think that you'd look at a star and you'd see the disk of a star look pretty small, but you can pick it out, and then you'd go and observe it again a few years later, and it would have moved. So you could try to look for something going from here to here. Not very big, but doable.
So it moves by more than the star is wide across.
Yeah.
Yeah. Okay, so that may be doable. But there's a problem, is that when I go out and I observe, at least in the telescopes I use, stars don't look like that. They look more like that.
So we're actually trying to pick up the difference between this and this.
Yeah, that looks a little harder.
So why do your images of stars look so blurry?
Well, unfortunately, life is not quite as perfect as it might be. Although stars are very small, the telescopes we use to observe them are very large. Here's the Anglo-Australian telescope up near Coonabarabran, Siding Spring Observatory. And you can see this 4-meter telescope is many, many tons of equipment that all has to be lined up to 1/10 of the wavelength of light you're looking at. And 1/10 of the wavelength of light you're looking at is like on order of 1/10 of a micron, or 100 nanometers. So you have to have hundreds of tons of stuff lined up to 1/10 of a nanometer. And that's not so easy. And that's just the beginnings of the problems.
And so if there are any imperfections in the exact shape of any part of a telescope, that's going to blow your image.
Yep.
But even if you have built a perfect telescope, and we're fairly good at doing that, you've got this bloody thing up here called the atmosphere. This is Mauna Kea Observatory, possibly the best observing site on Earth that we use at the moment. That's me in front of one of the telescopes up there. But you can see even at this high altitude, it's about 4,200 meters up, there's a lot of atmosphere above you. And this atmosphere is not all uniform. It's got bubbles of hot and cold air, which have a different refractive index, and they bend the light. This is called astronomical seeing, and that's going to blur your image.
So that's like the worst problem we have, really. But, okay, we spend a lot of money. We build telescopes in space. We get above the atmosphere. And the Hubble Space Telescope, of course, really is lined up to 1/10 of a wavelength, and it is above the atmosphere. Clearly, this should solve our problem.
But the trouble is, even if you put the telescope in space, there's a fundamental problem that comes from the wave nature of light. This is refraction. As the light comes in through the aperture of the telescope, it's refracted because of its wave nature, and that blurs the images. We'll talk more about this later in the course when we get on to direct imaging, but it turns out that even for telescopes in space, your images are going to be blurry at some level, not as bad as from the ground, but still pretty blurry.
All right, but okay, so let's say we have our star and it's blurry. I can take lots of data, and if I get enough data, I should be able to maybe overcome my problem, right? I just go through and I use the law of averages, and I just average. And so although it's really, really blurry.
Yeah, so here's the blur. So this is a cut through the image. So image like this, you might go across it and measure how much light there is in each pixel as you go across here, and you might get something like this. And if it's shifted, it might change something like that.
So it shifts a little bit, and it doesn't shift much. But let's say that instead of looking at a few photons, I look at billions of them.
Yeah. So you might be able to see that it's gone up a little bit on this side and down a bit on that side. And so even though the shift is a tiny fraction of the blurring, you might be able to measure it. But even here, there's a fundamental problem. The problem is that we can't get perfect profiles like this. The reason is that this profile, this is where you expect light to arrive. You expect lots of light in the middle and less going away. But quantum mechanics tells us that the arrival of light is a random process. What this actually is a curve of is the probability of a photon arriving here. Light comes in photons. They are more likely to be over here than down there, but the actual time when one arrives is a random process. So here's a simulation of that. Here's what a spectrum image like that might look like as you build up over time. And what you'll see is photons are randomly arriving, and they're more likely to arrive randomly over here than over there. But still it's random, and as time goes on you start building up something. But you can see, because of the random arrival of photons, you're getting very noisy data. It's not a perfectly smooth curve.
Right, and so here we have the star emerging, and there appears to be a bit of a background, because the sky, of course, isn't completely dark.
Yes, even in a dark moonlit sky, there's a glow due to molecules in the upper atmosphere. Even if you go into space, there's a glow due to dust in our own solar system. So you're going to get some background, and then on top of it, you're going to get the signal
this
coming
little
up.
funny thing like that, and you might think, well, that's funny, but that's just random. That's the way life is that the Poisson process, as we call it, gives you funny looking things. But Paul, we've sort of cheated here. This is a pretty faint star. Why don't we look at Sirius, the brightest star in the sky, and then our telescopes should be literally able to detect billions of photons a second. And so we should be able to get something that looks pretty close to our ideal case.
Yeah, what you saw here is when we had a very few photons, like here, it looked like almost complete noise, but as the number of photons builds up and up, it gets better and better. And sure enough, if you can get hundreds of billions of photons, which you certainly can looking at a really bright star like Sirius, then you will get back that very sharp image. The trouble is, you've got a picture, and you've got that very sharp image, but how do you know where your telescope is pointing exactly? You kind of... you may be able to measure very precisely, it's at pixel number 47.539 on my detector, but when you go back and observe 10 years later, which you need to because these are 10-year periods, your telescope is almost certainly pointing a little bit off, so the pixel will change even if it hasn't moved.
So you'll know exactly where the star is in your picture, but you won't actually have any idea where it's exactly on the sky.
So the way you normally solve this is you reference it against some other stars in the field. So if you had two bright stars very close together, you may not know exactly where they are, but you'll know where one is relative to the other one. The trouble is, the really bright stars where you get beautiful smooth data, like Sirius, there isn't another Sirius an arc second away from it.
Okay, so the fact that we have Betelgeuse 25 degrees away isn't going to help us too much.
No, you need the two to be so close they'd be on the same part of the same image. If they're any further apart, even the atmospheric blurring will move them differently around to muck you up.
Okay, so this sounds almost hopeless. So maybe we should look at the fact that the other idea, when the star is coming towards you, it has a velocity we might be able to measure. Maybe we can do better that way.
Okay, so let's calculate how big the shift in the lines due to the Doppler effect is going to be. So, what we really care about is, are there planets around normal stars, not as opposed to these weirdo pulsar planets? So Brian, how might we work this out?
Well, a normal star doesn't have this nice little pulse of radio going off at an absolute perfect cadence. So we're sort of stuck with stars like the sun shining. But when we think about the Earth orbiting the sun, then of course the sun has to move around a little bit, and so the sun and the Earth both go around the center of mass of the two objects. And so we expect a planet to cause its star to wobble a little bit. And so, although it may be very hard to see the planet itself, we can, of course, look at the wobble of the star.
So that's one approach. Go and look for a star that's wobbling in little circles. This would be the case if, like here, the orbit is pretty much face on. Another possibility would be if the orbit is more edge on.
So that adds a complication, because it's not going in a nice little circle now, it's going in some little ellipse on the sky.
But it also gives you another thing you could possibly measure, which is that this thing is moving towards and away from us. So now it's coming towards us, now it's going away from us, the star that is, coming towards us again and going away from us, and that could have a Doppler effect. So for example, if that's the normal spectrum of the star with absorption lines of some description, when it's moving away from us, that might get shifted over to here. Then when it's moving towards us, it might get shifted the other way. So what you might look is for small shifts in the absorption line wavelengths.
Okay, so that's two interesting ways that we can imagine going out and finding a planet going around a nearby star.
Okay, so I'll go and calculate how big these effects actually are.
Okay, so let's work out how big a wiggle we would expect from a normal planet around a normal sun-like star. So we've got a sun-like star and a planet. Now let's model this on our own solar system. So let's give this the mass of the Sun and give this the mass of Jupiter, because Jupiter causes the biggest wiggles in our reflex motion wiggle in our own solar system, simply because it's so big. And we'll put these at the same separation as Jupiter is from the Sun in our own solar system, a little bit more than 5 astronomical units out. Now, if you remember, we had an equation for the orbital period, which was the square root 1 over g 4 pi squared over m1 plus m2 r cubed. So if we plug in the mass of Jupiter, the mass of the Sun, and the distance between them cubed, we end up with a period of 11.84 years, which is indeed Jupiter's orbital period. Good to check. So that's the first worry. It's telling us that you can't just observe for a few months, like you could for pulsar planets, to find plausible planets around other stars. You're going to need to look for decades to see a full sine wave. That's worry number one. Now, how big is the reflex motion wiggle? Remember the equation for this is R1, the reflex motion wiggle of the star, is equal to R 1 over 1 plus M1 over M2, which, if you plug in everything here, gives us 7.8 by 10 to the 8 meters, which sounds pretty big. If you compare it to the radius of the Sun, it's about, the radius of the Sun is 6.9 times 10 to the 8 meters. So it's a little bit bigger than the radius of the Sun. So the Sun's moving a little bit more from side to side than its radius. But can we actually hopefully see that? Well, let's say we're here on the Earth and we're looking at a star over here that's moving in a circle by that amount. So 7.8 by 10 to the 8 meters. What angle does that make on the Earth? Because this is going to determine whether we can see it with our telescopes at angle theta. Now, this is going to depend on how far away the other planet is. Let's say it's pretty nearby a star, only 10 light years away. Remember, the closest star is just over 4 light years, so there are a few stars within 10 light years, not too many, but Most are going to be further away, but we could in principle do this. It's quite a nearby star. Now, if you remember, we can use a small angle approximation, which is that the angle in radians is equal to this, we'll call it R1, over the distance, let's call it D. So that's going to be about 7.8 by 10 to the 8, it's about 10 to the 9. Meters over 10 light years, which is about 10 to the 17 meters. And that gives us the angle in radians. To convert into something out of degrees, we have to multiply by 180 over pi. We would actually need to convert it into arc seconds, because it's going to be a very small angle in degrees. An arc second is 1/60th of an arc minute, which is 1/60th of a degree. So multiply by 60 times 60 to get into arc seconds. So it turns out for the reflex motion caused by something like Jupiter orbiting around a one solar mass star 10 light years away, we're talking about an angle of about 0.0016 arc seconds.